Math 287, Quest to College. I'm Joe Vasta, and this video we are going to cover both of these sections, 6.4 and 6.5, isomorphisms, and the matrix of T, which we kind of already covered, but we'll do another example. So our first problem is find an isomorphism from P3 to R. What is that? Okay. So the deal is we have to know what an isomorphism is, and that is what we're going to look at now. Let's take a look at a definition of isomorphism. T is a linear transformation that goes from vector space V to vector space W, and it's both one-to-one and onto. So if you've got that situation, then T is called an isomorphism. And we say that V and W are isomorphic. So we really can't say that those vector spaces equal each other all the time when you have an isomorphism, but you could put this sign right here, which means isomorphic. So all an isomorphism is the linear transformation is one-to-one and onto. So it's just a fancy word just to confuse people. So let's get back to our problem here, which asks you to find an isomorphism from P3 to something. Okay, so the way you want to approach these problems is you want to say, well, what is the dimension of P3? That has dimension 4. Now, for something to be one-to-one and onto a linear transformation, to be both of those, you have to go from the same dimension to the same dimension. So this also must have dimension 4. So there's two parts to this problem, really. We didn't mention this. One is filling in that box, and the other part of the problem is actually finding that isomorphism. So let's go ahead and fill in the box. So what Rn has dimension 4? Well, it's kind of a silly question. We know that it is R4. So our isomorphism is going to go from this vector space to that vector space. Okay. Now in your book, I believe they're not going to say from and to. On the exam, I will, because I think that's more descriptive. So your book should have done a better job. Your book says find an isomorphism between P3 and R4. And what's implied is that it must go from P3 to R4. So I will use from and to. So let's take a look at a general element in P3. A general element in P3 would be, well, P3, that happens to be polynomials of degree 3 or less. So a general element is ax cubed plus bx squared plus cx plus d. That is a general element of P3. Could we have written this differently? Yes. Sometimes people will write this as a plus bx plus cx squared plus dx cubed. Tomato, tomato. Who cares? As long as it is a general element. Now my isomorphism is a linear transformation, so I'm going to take that and map it to R4. Now there's lots of ways. There's infinitely many different isomorphisms you can think of. And sure, you can make it more complicated for yourself, but I'm going to try to make it very simple, and I'm going to use A, B, C, and D in a 4-tuple. So the most basic way to do that is to go like this. A, B, C, D. And we think we're done. So there's an isomorphism that's a linear transformation that is both one-to-one and onto. Now, how could I show that this thing is one-to-one and onto? What I'm going to do, we could do this really quickly, but if you pick such an obvious transformation here, you probably don't have to do this, but I'm going to go ahead and show one-to-one. And now how do I show a linear transformation is one-to-one? I set it equal to the zero vector. And really, I don't have much writing to do, because look what happens. That would mean A is 0, B is 0, because look at that. C is 0, and D is 0. So I'll write that down. A is 0, B is 0, C is 0, D is 0. So the kernel, now we're done with the problem, by the way. The kernel of this linear transformation is the zero vector from P3, which if you put zeros in for A, B, C, and D, it is just the polynomial 0. That's what the kernel is. And it has dimension 0. Now, the range we could do as well. I mean, now some of you are like thinking, well, why didn't you do null space and call space? We don't really have to here, because we just saw that all those A, B, and C, D has to be 0. Now, if you wanted to write the null space of some matrix, you can, but we're not going to do that. We know that the dimension of the kernel plus the dimension of the range has to equal the dimension of the domain, which is 4. That's from the general rank nullity theorem. So we know that this guy right here, the range has to have dimension 4, and it lives in R4, so the range has to be R4 itself. And so that shows ontonness. This up here shows one-to-oneness, and so this really is an isomorphism. Now, other possible answers could have been, you could have put a D here, C, B, A. Or you could have gone A, C, B, D. There's lots of isomorphisms from P3 to R4. Now, if you were super silly, you could have gone, the first coordinate is A plus B plus C plus D. The second coordinate is 2A minus 7B plus 8C minus D, and etc. So you could have made this linear transformation really complicated. The problem with going willy-nilly and just picking some random things for those 4 coordinates is then you might end up picking something that is not one-to-one. And so if you made both, or not both, all 4 of those coordinates really complicated, and you had to check to see what the kernel was, that would be a lot of work. So when you do these problems in your homework, just make it simple. Now, one other thing that we want to do for this problem, so we're done with this problem, but we want to use our new notation. We can say that P3 is isomorphic to R4. So if you can set up an isomorphism between 2 vector spaces, then those vector spaces are isomorphic. Now, what does this really mean? Let's take a look at another theorem here. It says that all n-dimensional real vector spaces are isomorphic to Rn. This is a very important theorem, because if I have any weird vector space that has like dimension 7 or dimension 4, I can set up an isomorphism to Rn. Why is that important? Because I can take all the vectors through the isomorphism, then do all my dirty work in R4, and then send them back, because an isomorphism also has an inverse transformation. And so that's quite a theorem. And that helps us. And you may have, when you were finding whether something in P3, a linear transformation going from P3 to M4 was 1-to-1 and onto or whatever, you may have felt like once you started writing matrices up that you were actually working in R4. And it's because there is an underlying isomorphism. There are many. Let's go ahead and do the next problem, which is problem 2. Now, we've done a lot of our work in 6.4. I think in 6.4 that's where they introduce 1-to-1 and onto, and I thought it was better to introduce it early on. Let S be the subspace, so that's a vector space within a vector space, the subspace of M3 consisting of skew symmetric matrices. Find an isomorphism from S to P sub something. So we have to figure out what that something is. Before we do, let's go ahead and put a representative of S up. So 3x3 matrices, skew symmetric. So we'll put a representative 3x3 matrix. For it to be skew symmetric, you have to have the main diagonal being zeros. Now we play this game. Am I free to put anything there? Yes, I am. I can put whatever I want there. I'll put an A there. So we're trying to write a general element of S, which is skew symmetric matrices. Am I free to put anything there? Absolutely. So I'm going to put the letter B there. Am I free to put anything there? The answer to that question is no, because you have to have the opposite element. So this is going to be negative A. Am I free to put anything at that spot there? Second row, third column. Yes, I am. I'm going to put a C there. Now, am I free to put anything down there? No, I'm not. I have to have a negative B. And I also have to have right here a negative C. So any 3x3 skew symmetric matrix fits into this mold. So there it is. So the deal is, what is the dimension of S? Well, I'm not going to do it right here, but if you were to splactor this, split and factor, you would have a linear combination of how many vectors from S? You would have a linear combination of 3 vectors. So that would make the dimension of S 3. See, there's 3 different letters, A, B, and C. So if you were to split and factor, which they did not ask us to do, by the way, that's why I'm not doing it, then you would have a linear combination of 3 vectors from M3. Okay, so this has dimension 3. This also, because we're looking for isomorphisms, must have a dimension of 3. Well, P sub what? Now we got to be careful not to just go P3. It's going to actually be P2. Okay, polynomials of degree 2 or less. That has dimension of 3. So let's go ahead and finish up this problem. We're going to say T of these creatures. Now what your book is going to do, and that's all right, is they're going to put parentheses around the matrix. Now if it were a polynomial, I would put parentheses around it, but lots of times you'll see me not put parentheses around a matrix when I'm doing a linear transformation. I'll just say T of that matrix. Okay, maybe that's a bad habit on my part. It's laziness, really. Okay, so now we are going from S, which looks like this, to polynomials of degree 2 or less. So how am I going to do this? Well, I need to use A, B, and C. And so the most obvious way is to say AX squared plus BX plus C. If I set that equal to the 0 polynomial, then I would have A equals 0, B equals 0, C equals 0, which means the kernel has to be the 0 vector. So there it is. Now, are there other isomorphisms? Yeah, we could have said A plus BX plus CX squared. We could have even gone all crazy and said the coefficient here would be like A plus B minus 7C, and the coefficient here would be A minus B plus 20C. And, you know, you could do that, but then you would have to verify, you would really want to verify that it was one-to-one and onto. So here is the answer. Many answers possible. And so what can we say about those two vector spaces? This vector space, which is really a subspace of M3, and P2. Well, we can say that they are not equal, okay? Because we can't say matrices equal polynomials, but they are isomorphic. And so you don't have to write that. You just have to find the isomorphisms when you are doing your homework. Okay, so let's go ahead and take a look at our next theorem, if I can find it. Here it is. This is the invertible matrix theorem, which keeps growing. I think we started off this with 4 or 5, and now it's up to 11. Your book makes it go up to like 18, but they put some conditions in there that I think are kind of extraneous. They're true. I stuck with the important stuff. You have an n by n matrix, so this is just 4 square matrices with real elements. You have a linear transformation. Oh no, this is a linear. Be a matrix transformation. Okay, so this is a matrix transformation, which, you know, we could say linear transformation, and it's defined T of x equals AX. Okay, so you've got a linear transformation. The following conditions on A are equivalent. So here's the first one. A is invertible. And I always like to jump down to condition 5, which means it is row equivalent to the identity, which means the rank is n, which means AX equals B has a unique solution for every B in Rn, and AX equals 0 has only the trivial solution. So these are things we've seen before. Well, if A is invertible and it's row equivalent to In, the determinant does not equal 0. A transpose is invertible. The nullity of A is 0. I think we've seen these ones. The call space of A is Rn. The row space of A is Rn. And then here's the new one right here. T is an isomorphism. So the problem that I'm going to show you just illustrates this theorem. And I was actually going to do this in 6.3. But I felt like 6.3, the video being over 2 hours, this would have just been it. That would have been the breaking point, and people would have gone crazy. So I decided to include it here, which really is in 6.4. This is number 3 from the 6.3 lecture. We went from R2 to R2 using this transformation, okay? Which is actually row equivalent to that matrix. And we found that the kernel was 0, 0, and the range was R2. So the dimension of those add up to 2, which is that's the rank nullity theorem. And we found that this linear transformation was 1-to-1 and onto. Well, it illustrates this theorem. This matrix here is invertible. The determinant of this matrix is 4. And all these things that we say apply to this matrix here, with the last one being T is an isomorphism. The row space is R2, the call space is R2, etc. The nullity is 0, the rank is, let's see, I'm looking at the nullity here, the rank is 2. And so what are we to do with this example? Nothing much. I'm just saying that this illustrates the theorem. Okay, so I'll just say C theorem. Which theorem is this? This is the invertible matrix theorem. I'll just say with 11 conditions. Okay. Do we have to memorize all these conditions? No, not in this class. Now, if you were taking this for a math major, linear algebra for math majors at a university, yeah, then you dig deeper into the theory. You do more proofs. Okay, so this really, we're not doing anything with this problem because we've already done everything in the last lecture. So that is what we have there. Let's move on to some other things here. This right here. V and W are vector spaces with ordered bases. There they are. And T is a linear transformation. The M by N matrix. So we've done this before in an example. This is called the matrix representation of T. Relative to the bases B and C, looks like this. Okay, so that does look intimidating. And when we find this, we're not really looking for component vectors. We're actually just setting up the matrix we normally would when we find the kernel. But technically, you can do it this way. I am going to do a problem that comes from 6.5, something that I made up, and we're going to be asked to find this matrix representation. So that's what I'm going to do next. So here it is. You've got a linear transformation going from 2 by 2 matrices to polynomials of degree 2 or less. Real coefficients here and real entries in the matrix. Your linear transformation looks like this. T of A, B, C, D looks like that. Okay. You have an ordered basis for 2 by 2 matrices, and it's E11, E12, E21, E22. It's what you might expect for 2 by 2 matrices. You have an ordered basis for P2, which is 1, x, x squared. And in some ways this is good they wrote it like this, because look, this is times 1, this is times x, this is times x squared. So it's kind of written in the same order as our linear transformation. Find the matrix representation. So we're trying to find our matrix of T for something that goes from matrices to polynomials. So can we do that? I think we can. So what I would do is, I'll do this in a different color. I would set this linear transformation equal to 0. The 0 vector of P2 is just the polynomial 0. Okay, so I set this thing equal to 0. So what does that say? It says that A minus 2B minus 5D must equal 0. It also says that 2A minus C minus 4D has to equal 0 as well. And then also, A minus B plus C minus 6D, that's in front of the x squared, that has to equal 0. Now, if I were good, I would have lined everything up. Look, the B's right above the C, etc. Okay. So basically, to find the kernel, I must solve for A, B, C, and D here. Okay, and that's going to describe the things that go to 0. Okay, A, B, C, D. Now, what I'm going to do is I'm going to draw the augmented matrix, except I'm not going to put the 0 column in. So watch this. This is 1, negative 2, 0, negative 5. Okay. Now I'm not putting the 0 in because I'm trying to find this matrix of T, and this is the first row of it. The next one is 2, 0, negative 1, negative 4. Okay, so that represents that equation, and then without the 0 there. And then the last one is 1, negative 1, 1, negative 6. So we've been calling this the coefficient matrix. of this system. That's what it is, matrix A. And before, well, actually, let me put a box around it. But let's just check if we've got everything correct here. This column came, it represents A. It came from the A's. Okay, see there's a 1A, 2A, 1A. Now A happens to represent the element that's in the first row, first column, or the one that corresponds to E11. And then this right here is B. Notice, here's negative 2B, there's not a B there, so there's a 0 and then a minus B. B is up in the first row, second column, which corresponds to E12. And you can see that this one is E21, that represents C. And then D is E22. Now the rows, look at the first row. How did we get the first row? We set that thing equal to 0. Now there's actually a 1 there. And so that's the one that kind of went with 1 there. And then this right here, this equation, second equation, that was the coefficient of the x. And the third row gels up with this equation, which is the coefficient of the x squared. X squared. So sometimes when I'm finding the matrix representation and doing these problems, I look at my ordered bases and make sure the ordered basis B is in the same order up there. And then make sure the ordered basis C, 1xx squared, is in the same order right there. And if it is, then I have just completed this problem right here. There it is. So that is done. Let's go ahead and take a look at a few other things. Okay. If V is Rn and W is Rm, and they are equipped with standard bases, then this matrix representation of T is just the matrix of T defined earlier in 6.1. Okay. Last two theorems right here. If V is W and T of V equals V for all V and V, then this matrix representation is just the change of basis matrix from B to C defined earlier. So if the linear transformations, sometimes we call this the identity transformation, then you just have change of basis matrix that we have defined when we're doing change of basis. Theorem. So you can say T of V, which is written as a component vector, equals this matrix representation times the component vector of VB. Now we're not going to illustrate these theorems. These are just some theorems in the book, and if you're a math major and you have to take linear algebra for math majors at a university, you'll get more into this. But there's a lot of neat connections you can do with component vectors and, you know, change of basis matrices and linear transformations. Okay. What we're going to do, and I think this is going to be more important than like exploring those theorems, is we're going to look at this example here that we just did, and just for practice, we're going to find the kernel, the range, dimensions, is it 1-to-1, is it onto, the general rank nullity theorem, and T inverse. So that's what we're going to do. So let's take a look at this up here. So that's what we'll do. So remember that our transformation is going from M2, and I'll abbreviate without the R. This is to P2. This matrix is the one that we just found that looks like this. 1, 2, 1, negative 2, 0. So what I'm doing is sort of a review of what we've been doing in this chapter. Okay. Now before I move on, I want to first point out the dimension of M2, that's 2 by 2 matrices, is 4, and the dimension of P2 is 3. What am I actually trying to find on this matrix? So I know we kind of lost the other paper. We are really trying to find the null space of that matrix. You know, put some zeros there, like I'll put them here in red. And then what do we have to do with that matrix? We have to do row operations. So I'm actually going to do the row operations for you. I ended up getting 1, 0, 0, negative 3, 0, 1, 0, 1, and then 0, 0, 1, negative 2. I actually put this matrix in reduced row echelon form, and of course these zeros right here that are in red, they're zeros as well. They're right there. And the letters, the variables, were A, B, C, D. So what I'm trying to find now on this matrix representation is the null space of the matrix representation. Even though null space is not up there, that's going to help me get the thing that I'm trying to get. The other thing that was from the last page, let me put it here. E11, E12, E21, E22, and then this is 1x, x squared. Okay, I have bound, bound, bound. So A, B, and C are all bound, and D is free. So if D is free, we'll say that D is T. Now, third row gives us that C is 2T. And second row gives us that B is negative T. Now if you're going, whoa, Joe, what's happening? The second row says B plus D equals 0. B plus D equals 0. B plus T equals 0, so B is negative T. The first row gives me the equation A minus 3D equals 0, A minus 3T equals 0, A equals 3T. Okay, so we're a little bit more efficient in terms of finding null spaces than we used to be, maybe, if you've been doing your homework. So let's go ahead and do the null space of this matrix. Okay, so I'm going to write that down. So inconvenient to write, but I want to write it down here. Well, if you list this off as an ordered quadruple, you end up getting 3t, negative t, 2t, t. And you splactor, which is really just a factor, you get t times 3, negative 1, 2, 1. So that is the vector that we have there. There's only one. It's a linear combination of one vector, so the null space is going to be the span of just that one vector, which is 3, negative 1, 2, 1. Now they didn't ask for that, but that's going to help me find the answer. I want to show you something that I didn't show you. This is something you can do when you find a null space. Is you can say, well, really, I can write this as a column vector and then multiply it by that and see that I zeroed it out. But the same thing is by going like this. See where my pins are pointing? I multiply those together, so that's 3 plus 2, because I'm multiplying negative 2 and negative 1. So 3 plus 2 is 5, and then we have 0 minus 5. That zeroes out the first row. if it's in the null space, it should zero out all 3 rows. Watch this. 6 plus 0, so I'm at 6, and then minus 2 minus 4 zeroes it out. And then look at this one right here. This is 3 plus 1 is 4 plus 2 is 6, and then I have minus 6, so it zeroes that out. And really all I'm doing is I'm saying this matrix times that column vector equals the 0 vector. Okay? So sometimes I visually check after I find the null space to make sure that happens. Now remember, this vector right here is a 4 tuple, and this one kind of corresponds to E11 in our linear transformation. This is E, so I'm using the same order, E12, E21, E22. So when asked for the kernel of the linear transformation, and we know the kernel lives in M2, so it better look like 2 by 2 matrices, it's going to be the span of just one element, just like the null space was the span of one element, and it's not going to be written as a 4 tuple, it's going to be written as a 2 by 2 matrix, and we're going to use this as our guide, the E11, E12, so this goes in the E11 spot. I mean, it's really 3 times E11 minus 1 times E12, etc. It's going to give me this 2 by 2 matrix. 3, negative 1, 2, 1. So you plug that or any multiple of that into this linear transformation, you'll end up zeroing out the linear transformation. It will end up taking that element to the 0 polynomial. So it's important on the exam, if I give you a problem like this, find the kernel of the linear transformation, you don't just say span of this 4 tuple, because this is something from R4 and the kernel should live in M2. Okay, now they wanted the range, but before we do the range, I'm going to show you another cool thing that we can do. The dimension of the kernel is 1. Also, that tells me something about one of these guys. It tells me that it is not, the linear transformation is not 1 to 1. Now the range. I'm going to use the general rank nullity theorem, and I'm going to figure out what the dimension of the range is before I actually do it. The dimension of the range, well, these dimensions have to add up to 4. So the dimension of the range has to be 3. 1 plus 3 equals 4. Now here's the cool thing. The range lives where? In P2. P2 has dimension 3 as well. So the range is P2. And we got that from the general rank nullity theorem. Now, if you're thinking, well, Joe, no, I wanted to find the call space, then the call space of this matrix would be the first 3 columns. You would write the span of those. Well, you'd have the span of a basis in R3 that has 3 elements, which would be all of R3. Which, when you went to translate it to P2, you would have 3 in a basis in P2, which would give you all of P2. So this was the quick way of doing it. If you didn't think of doing it that way, you could still get the answer. Now, kernel range dimensions, 1 to 1 onto, okay, so the dimension is 3, and it matches the dimension of the codomain, so this is onto. General rank nullity theorem, we use that. 1 plus 3 equals 4, which is that right there. And T inverse. T inverse, well, the only way you can have an inverse linear transformation is if your transformation is both 1 to 1 and onto. And it's not 1 to 1. So T inverse does not exist. And that completes section 6.4 and 6.5. You guys have a good day, and I'll see you on the next video.